Alright, so while I'm waiting for my stylus, I figured I'd talk about some of the introductory stuff related to probability, and I'm going to illustrate it using this Desmos graph that I have to write over here. Um, and something I noticed about the last few videos, and I apologize for this, is that I have not been um, adjusting the text that you can see underneath here, and so this time I have. And we could see the topics that I intend to cover in this particular video, just introduction to probability, and then we'll talk about union and intersection of events and or like and slash or events, uh, conditional probabilities, the basic rules about these things, and then the concepts of independence or disjoint. All right, so let's first take a look over here. So essentially, um, what a probability is, and we often denote it as, P of something is equal to some value. Uh, in this case over here, what A is, this is a function, but it's not a function in the traditional sense that we've seen them previously, where the inputs are numbers or unknowns and the outputs are numbers or unknowns. Here, what goes into the argument of our function, so what A and B and these other statements are statements are statements. They're statements or they're events. They're descriptions of things. So maybe people are eating at a restaurant and there's something wrong with the food there. So event A here is the probability that a guest orders, say, seafood, and maybe probability B here is the probability that someone eating the food at this restaurant gets sick. And so, of course, what we have is there are 60% of the people who eat at this restaurant got seafood, 40% of the people who ate at this restaurant got sick, and of course, there's some amount of people here who both ate at the restaurant and got sick, and there's some, who here say ate seafood, sorry, ate seafood and got sick. Here are some people who ate seafood and didn't get sick, and over here we have people who got sick but didn't eat any seafood. All right. And so the arguments here are events, and the outcomes are like a proportion of outcomes that would, the output is a proportion of outcomes which satisfies the event. And so, like I said, in this particular case, it would mean like some percentage of people got sick and or ate seafood and got sick respectively. And so the outputs of the probability function range from 0 to 1. 0 meaning that the event is impossible, and 1 meaning that the event is guaranteed to happen. All right. So we know from uh, reading section 1 in chapter 2 that given two events, it's possible for there to be operations between them. Just like, if you have two numbers, there's operations between them. We can add them, we can multiply them. There are others, of course. And so we have events A and B. There are some natural operations that occur there. And so the two ones that we'll start with here are the union or operation and the intersection and operation. And so what we have here then say is the event A and B is itself an event, and that describes the event that a person ate at this restaurant, they got the seafood, and they got sick. And the event A or B, again, it's a combination of two events, which is itself an event, and this particular event describes anyone who either got seafood or got sick. All right. So we could see here that that 60% of the people got seafood, 40% got sick. And one of the questions on the homework is if we ignored the green and the purple line here and we just knew that 60% of the people got seafood and 40% of them got sick, is that enough to know either how many people got seafood or got sick, or how many people got seafood and got sick? And it turns out that that's by itself not exactly enough information to know. So, for example, I can keep these two values the same, but it's possible for me to set this up so that 100% of the people who came to this restaurant either got seafood or got sick. None of them got both, and all of them fall into either one group or the other. On the other hand, as I scooch this over, we could see that it's possible for, well, an extreme case, that the only people who get sick are those who ate seafood, right? And so in this case, if I say, oh, who got seafood or got sick, it's only the same 60% of people did one or the other. And who got seafood and got sick? Well, since the only people who got sick ate seafood, then saying you ate seafood and got sick is the same thing as saying you got sick. So it is just the same 40%. And of course, there's a bunch of intermediary sort of possibilities, right? It just depends on how many people uh, both ate seafood and got sick. So let me try to set it up to, oh, I almost had it. There we go. To where it was before. So here we have 20% of the people, of the restaurant goers, ate seafood and got sick, and 80% of them ate seafood or got sick. All right. So if we knew two of these things, so if I knew the 60% and this 40%, and I knew, say, for example, that 20% of them were in both camps, is that enough for me to determine how many people ate seafood or got sick? And the answer to that is, if I knew just these two, that wasn't enough. If I also knew this, that does turn out to be enough. Because what that means is that, all right, 60% of people ate seafood, right? And that includes these people here who got sick, and so that, which is 40% of people. And so there's another 20% over here uh, who got sick who didn't eat the seafood. And so it helps maybe to concretize this. Let's say 10 people came to this restaurant. 6 of them ate seafood, 4 of them got sick, right? And 2 of them ate seafood and got sick. So how many people either ate seafood or got sick? If I just add together these 6 people with these 4 people, that would be 10 people. But we should note that the 2 people here in this A and B category, they're counted twice, right? So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these 2 people here, which are these 2 people here, they got counted twice. And so if I want to figure out how many people ate seafood or got sick, I have to add together 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then remove the 2 that I counted twice. So it's just 1, 2, 3, 4, 5, 6, 7, 8. And that's what gives rise to the general addition rule. So this is from the textbook, right? The probability of A or B is probability of A plus the probability of B minus the intersection of those events. All right. And so similarly, if you knew the probability of A and the probability of B, and how many people were in both, then you could find, or in one or the other, you could find how many people had to be in both events. And in general, this is just a linear equation, right, with four unknowns. So if you can fill in three of these, then you'll automatically be able to fill in the fourth one as well. All right. So let's talk about conditional probability again. And so let's say what conditional probability refers to. So I'm going to scroll down on this side here. Let's take this first one. A given B, what A given B means is that if you know that event B happens, what is the probability that event A also happens? So so for example, in this context, what that means is if you knew that someone did get sick, what was the chance that they were eating fish? And again, it helps to concretize this. So let's say again, we have 6 people total who ate seafood or ate fish, 4 people who got sick, with 2 people in the overlap, and then 2 people out here who neither uh, ate seafood or got sick. So if you knew someone got sick, that means they're one of these 4 people here, 1, 2, 3, 4, and it looks like 2 of them ate seafood, 2 of them did not, right? And so it seems as if you're given B, if you assume that you're only talking about people who got sick, it appears as if half of them, or 2 out of 4, ate seafood. And if I click on that, yep, we could see the projection of the seafood eating people onto the the group of people who got sick, and we can see, all right, yes, 2 out of 4 is in fact a half. And so we know that, oh, uh, if there's less of an overlap between people who ate seafood and got sick, then if you assume that someone did get sick and you only focus on those people, then less of them ate seafood. If the overlap is greater, then all right, well, we have P of A given B here, then, right, what we have is that 100% of the people who got sick ate seafood, but that's because my probability B here is sitting squarely inside of the event A. All right. So the way we want to think about that then is what percentage of this group is this group here? It's simply the size of this group out of the size of this group. Just like the probability of A is the size of that group out of 100%, right? And so that gives us a general rule for conditional probabilities. And this is, you can find in section 2.2 of your text. And that gives us this particular formulation here, right? So the conditional probability of the outcome of interest A given condition B is computed as follows, blah, blah, blah. And all this is trying to say is, all right, it's the size of the group of people who are both A and B out of the size of B, right? And that's all this is. And that's all how this number here is computed, right? So let's move things back just slightly. Yeah, there we go. Okay. Right. And if we want to switch it up and say, okay, given A, what's the probability of B, then, right, again, we see, okay, out of these 6 people here, out of these 6 people here, 2 of them, so 6 people had seafood, 2 of them got sick, so, 2 out of 6 or 1/3 of the seafood eating people got sick. So uh, that's that. Okay, so let's talk about what it means then to be independent. The best way to think about independence, so 2 events A and B are independent if knowing the outcome of A doesn't affect the outcome of B or vice versa, right? So uh, my favorite example of 2 independent events is flipping a coin and the chance that I get a heads, and crossing a street and the chance that I get hit by a bus. So if I flip a coin, there's a 50% chance I get a heads. Now, if I go and cross the street and I get hit by a bus, and while I'm lying there on the ground, I take a coin out of my pocket and I flip it, the chance of me getting the heads is 50%, right? It was not affected at all by the probability that, uh, by the fact that I was hit by a bus. Those 2 things didn't influence each other in any way. And so the best way to think about independence in the language that we've been describing here is that um, if A and B have no influence of each other, then the probability of A is the probability of A. And if I'm given B, that shouldn't change the probability of A, right? The probability of A should remain the same. So one way to think about this is that the probability of A given B is the same as the probability of A. And similarly, it should go the other way as well. So the probability of B given A should be the same as the probability of B. Now, so let's take a look at our current setup here. We have some people eating seafood, some people getting sick. Are these events independent? And well, we can go ahead and remind ourselves, right, that out of the 6 people who ate seafood, a third of them got sick, right? 2 out of 6. But the probability of getting sick in general is 40%, right? So I'm looking at this, I'm like, hey, if you ate the seafood, you actually had a smaller chance of getting sick than the general population of the restaurant, right? So overall in this restaurant, 40% of people got sick, but out of the seafood people, only 33.3 repeating percent got sick. So they are actually a little bit better off than everyone else was. So clearly, whether or not you ate seafood has something to do with whether or not you are sick. They're not like divorced from each other. One of these events does have some influence on the other, so we could see that they are not the same. And similarly, and so they're not independent, right? Because if I know that I ate seafood, I know my chances of being sick are less than otherwise. And the reverse is true as well. If I go A given B, so okay, over half the restaurant got seafood in general, but out of the people who got sick, exactly half got seafood. So if I know someone got sick, I know their chance of eating seafood is a little bit less than it would be otherwise. So again, there's some influence of these things from each other. And well, so I could adjust this slightly, so in maybe a slightly different restaurant. Let's say where the overlap between the two events is 0.24. So let's say there's 100 people at this who ate at this restaurant, 68 seafood, 40 of them ate, uh, 40 of them got sick, and then 24 of them is this overlap both, right? And so looking at this, I can say, well, 60% of the people ate seafood, and if I look at the people who got sick, 60% of them ate seafood. So it didn't matter, right? It doesn't make a difference. Definitely, the probability of eating seafood is 40% no matter what, right? And if I were to flip this around, right? Okay, so 40% of the restaurant got sick, and of the people who ate seafood, 40% of them got sick. So it makes no difference, does it? Whether or not uh, you ate seafood or not, you're going to get sick 40% of the time, no matter what. And since it doesn't make a difference, that's what makes these two events. In this case, they're independent. So one thing that we could see when it comes to independence is that there's a bunch of ways you could try to test to see if two things are independent, but the main ones are, again, that the probability of B given A is the same as probability B because A made no impact. The probability of A given B is the same as the probability of A, again, because B made no impact. And so one last note is that, and let me turn this off here. The probability of A and the probability of B, that the intersection of those events, that the probability of A and B happens, is simply the product of the two probabilities. So that's the third test, right? So 0.6 times 0.4 is 0.24. And this follows from a fairly straightforward algebraic derivation, which is in a handout I wrote in D2L. So you can go check that out if you want to see the details of that. But the basic idea is that, all right, 60% of people say ate seafood no matter what. So if I take the 40% of people who got sick and I took 60% of them, that's the people who ate seafood and got sick. And you can go the other way. 40% of people get sick, so 40% of the 60% is 0.24 if they have no influence on each other. And then otherwise, either you're more likely to get sick when you ate seafood or you're less, right? It's only at 0.24 that does make a difference. Okay. And then the last thing on the list of things I want to talk about in this video is what it means to be mutually exclusive. And so two events are mutually exclusive or disjoint if there's no overlap between them. So the probability of A and B is 0. Now, sometimes people confuse mutually exclusive and disjoint with independence. And we could see in this case that these two events being mutually exclusive or disjoint definitely makes them not independent. So in this case, like 60% of people ate seafood, 40% got sick, and there's no overlap between them. So everyone who ate seafood was fine. Every single person who didn't eat seafood got sick, and vice versa. So, in general, 40% of people got sick. If you ate seafood, what percentage of them got sick? And you can just tell looking at this right away, but it's 0, right? No one who ate seafood got sick in this case because there are no people who both ate seafood and got sick. So if you knew someone ate seafood, could you then does it make a difference whether or not you ate seafood or not? Yeah, of course it makes a difference. It's literally the only thing that determines whether or not you got sick was whether or not you ate seafood. So of course it makes a difference. And if two things make a difference on each other, then they're not independent. All right, so hopefully that helps with some of the questions in chapter two. Um, I'm gonna follow up with some more conditional probability stuff and Bayes' theorem.